Okay, so back to circuits. Okay, how does laundry and circuits work? So here's a combinational circuit. The X input goes to the F and G modules, and the output comes out, and they feed forward their results to the H module, and then the output, the processing of X, comes out of the H module. And so there's a propagation delay, which is the longest path from X to P of X through the circuit. And in a combinational circuit, we compute the latency as just the TPD of the combinational circuit, and the throughput is always 1 over the latency. In other words, we can produce one answer every TPD seconds. We have to wait at least TPD to get the first answer out, and then if we get started right away, we have to wait another TPD to get the second answer out, and so we're getting one answer every TPD seconds. If we make a graph of what's happening sort of in time, so at a certain time we apply a new input X. And then after the propagation delay of the F module, we get its output. And after the propagation delay of the G module, we get the output from that module. And in fact, there's no particular reason why they would be the same. Usually they're not. They're different processing, different TPDs, different circuits inside of F and G. After the second of the two outputs is available, H now has a set, all of its inputs are now stable. Both the F input and the G input are stable. And so we can wait the propagation delay of the H module, which we see sort of from this time point all the way to here, and finally we get our answer. But we notice sort of after the F and G outputs are stable, that the F and G modules really aren't doing anything very productive. Their only job is to sit there and hold hold their outputs stable so that H can do its job. And as it turns out, we actually have a circuit that's particularly good at holding a value stable. Okay, we could use registers. And so if we basically insert registers into the circuit, and here I've shown you registers that sit between F and G, and the job of those registers will be to hold the values of F and G stable so that A can do its job. And by the way, once we put those outputs, F of X and G of X, into a register, F and G can get started on the next input. They no longer have to sit idle, okay, while H is doing this job. So if you think of these as washers and this is dryer, right, we have a two-stage pipeline that's sort of working for us. So this is what's called a pipeline circuit, where what we've done is to divide the total processing that we want to do into a set of pipeline stages. And the stages are separated by registers. And by convention, as I'll say again in a second, we always put a register on the output. And the reason that we have that convention is that once I've designed a pipeline circuit, suppose I wanted to compose two of these in a row. You can see by having a convention of, look, we always put a register on the output, that I could now make a second copy of that circuit. So P of X could go into another copy of this FGH processing pipeline. And in fact, everything would just play along. In other words, the notion, because that output register would then be the register between stages as I compose it to larger and larger things. So our rule of always placing a register on the output allows us to sort of use our tinkertoy approach of building together larger pipeline circuits from smaller pipeline circuits. Okay, so let's think a little bit about how fast can we clock this circuit. So unpipelined, we had a latency of 45. That was the longest path here from G to H. We could either go from F to H and out, or from G to H and out. The longest path is the sum of G and H, which is 45. So in the combinational circuit we started with these timing numbers, the throughput was 1 over 45, and the latency was 45. With a two-stage pipeline, well, how fast can we clock this circuit? What we have to do now is to do the timing analysis that I reminded you to have engraved on your hand, which is we have to look at the propagation delay of the upstream register, the combinational delay, the TPD of the logic, plus the setup time of the downstream register. Now, in this case, and as often the case in our pipelining problems, we assume fantastically good registers that have 0 propagation delay and 0 setup time. But that extra complication of accounting for those is very straightforward, and you already know how to do that. But since we're sort of now trying to focus more on latency and throughput, we're not going to complicate all of our arithmetic by adding in those 2 extra pieces of propagation delay and setup time. So assuming ideal registers, we have to look for now in each pipeline stage, the longest path from a register output to a register input, or from a circuit input to a register input. And in this case, that's 25, the H module. So that means that we can clock this circuit at 25 seconds, nanoseconds, whatever it is, 25 time units. And it takes 2 clock cycles, okay, to finally have the answer appear at the output. So the latency is 50, but we get a new answer every 25 time units. Or excuse me, yes. So the throughput is 1 over 25. Everybody sort of happy with that? And now you can see why, when is it we could come up with sort of a perfect thing where increasing the throughput would not affect the latency. In this case, the latency got longer. So if looking at the circuit, you can say, well, it's sort of inevitable the latency got longer because there's a little wastage involved because we had one module that was slower than everybody else, and that's what set up the pipeline. So what would be an ideal situation? Yes, sir? Right, so if all the modules sort of had the same TPD, then we'd have a clock period where every pipe stage, was exactly, it was fitting like a glove, the clock cycle and the delay of the combinational logic. And in such cases, we would discover that the latency would not get worse when we pipelined it, but the throughput would just get better. Okay, any questions so far? I mean, my fingers have never left my hand, but now we've produced a circuit that with a small additional cost of these registers is actually performing, it's not twice as good, but is actually getting a lot more answers out per second. Yes, sir? Can you explain again why you have the latency there? Okay, so let's think about the pipeline stage. So we're allowed to clock these registers once every 25 nanoseconds. In other words, we're going to use a single clock for all the registers. And we pick the clock period to accommodate the slowest pipeline delay. It wouldn't really do us any good to try to clock this guy sooner because these registers can't get a new input until this guy is really done, right? So we have to move everybody forward through the pipeline sort of in lockstep in order for the pipeline to work correctly. And so the period it takes in this case is the period that would accommodate the slowest pipeline stage. So in this case, we actually have to run the clock at 25. So let me stop there. Are you happy with why we had to choose 25 for the clock? Yeah. Okay. So now if you think about how many clock cycles does it take for an X input to be reflected on this output? Well, it takes 2 such clock cycles. The first clock cycle, we capture the intermediate result in that register, and at the end of the next clock cycle, we capture the output in the output register. And so that means it's taken us 2 25 nanosecond clock cycles to get the answer out. So the entire latency from start to finish is 50, 2 clock cycles. So the latency of a pipeline circuit is always the number of stages in the pipeline times the clock cycle. Okay, is that, so we've made our circuit faster. So in fact, the processors are, in a sense, so fast because we've managed to break the processing of instruction into lots of little steps. So the entire instruction still takes some amount of time to process. The latency for an instruction in your CPU is high. Okay, but the throughput of your processor is very good. In other words, by breaking things into lots of little steps, most of which run in parallel, or in pipeline fashion, we can be working on 20 instructions at a time, and voila, your processor runs faster. It turns out there's some complications we have to solve, and in fact, the last 2 or 3 lectures of the course are devoted to figuring out the complications of a pipeline processor. Okay. So it can be a little complicated to keep track of all the things that are happening in a pipeline system because we're actually doing lots of things at the same time. And of course, that was our goal. So what we've done is we've developed this pipeline diagram, which is really pretty simple. Down in the rows of the diagram are the various pipeline stages. sort of show us all the sequences processing. We have an input, and then we sort of do the first phase processing, and then we have, so the input to the first stage is the input to the circuit. The input to the second stage is the output of the F and G registers, and here the input, if you will, to any subsequent processing is the H register. So these are the pipeline stages here. And then going across the top, we have successive clock cycles. So if we think a little bit about how the diagram works, there's three questions we can answer to the diagram. One is that we can, in fact, follow any particular input as it gets processed by the diagram. So during clock cycle I, I'll call it 1, just to make it easier to say. So during clock cycle 1, the X input is X sub I, X sub 1 is sitting on this wire, and during clock cycle 1, F and G are doing their job. At the rising edge of the clock that separates clock cycle 1 from clock cycle 2, we'll basically latch the output of the F and G modules into the registers. And now, during clock cycle 2, the registers, the inputs to the H module are F of X sub 1 and F of X sub 2. And then finally, during clock cycle, during the second clock cycle, we do all this processing. At the rising clock edge that separates clock cycle 2 from clock cycle 3, we finally latch the output into the register that's on the output of the H module. And then you can see that after 2 clock cycles, the output of this entire pipeline circuit reflects the input that happened 2 cycles earlier. So the output that happened, say, during cycle 1 is available on the output at cycle 3, at the beginning of cycle 3. So it took 2 pipeline stages, two clock cycles to get that. And you can sort of see that a particular input value moves diagonally through our pipeline diagram. We can also say at any particular clock cycle, what's everybody working on? And you can see that we have successive generations of data that are in different stages of the pipeline at a particular clock cycle. We can also look to see what a particular functional unit is doing over time. So if we look at a row, we can see that we can sort of look at for instance, what the H module is working on at any given time. So it's always working on the output of the F and G registers, and you can sort of see what values it's working on. So we have this vertically, horizontally, and diagonally. We can get a lot of information from the pipeline diagram. Sort of helps us keep track of all the things that are happening. And you can say, well, it's not that complicated, Chris, but if you imagine these are instructions being processed by a processor, you can see that there may be some complicated interactions that we'll have to think about. And again, as we get towards the end of the course, we'll find that the pipeline diagram is instrumental in figuring out what's going on and what we have to do to make it work right. But for this simple thing, I just sort of introduced this as sort of a graphical way of keeping track of what's happening when in a pipeline circuit.